The twin paradox is one of the most famous thought experiments in physics. It was first proposed by Albert Einstein as a way to illustrate the peculiar effects of his theory of special relativity. Imagine two identical twins. One stays on Earth while the other travels into space at nearly the speed of light. When the traveling twin returns, they find that they are younger than the twin who stayed on Earth. This scenario challenges our conventional understanding of time and forces us to rethink what we know about the universe. It highlights the strange and counterintuitive nature of Einstein's theory of special relativity. According to this theory, time is not a constant, unchanging entity. Instead, it is flexible and can be stretched or compressed depending on the relative speeds of observers. This means that time can pass at different rates for different people, depending on their motion through space. Special relativity deals with the relationship between space and time, particularly at high speeds. When objects move close to the speed of light, time behaves in ways that are completely alien to our everyday experiences. For the twin traveling in the spaceship, time slows down relative to the twin on Earth. This effect, known as time dilation, has been confirmed by numerous experiments and is a fundamental aspect of modern physics. The twin paradox forces us to confront our everyday understanding of time and grapple with the mind-bending idea that time is not absolute, but relative. This realization has profound implications for our understanding of the universe. It suggests that our perception of time is deeply connected to our motion through space, and that the universe is far more complex and fascinating than we might have imagined. The paradox has captured the imagination of scientists and the public alike for over a century. It has sparked countless debates, discussions, and further research into the nature of time and space. The twin paradox is not just a theoretical curiosity, it has practical implications for our understanding of the cosmos and the development of technologies that rely on the principles of relativity. It has been the subject of countless books, articles, and even movies. Popular culture has embraced the twin paradox as a way to explore the mysteries of time travel and the nature of the universe. From science fiction novels to blockbuster films, the twin paradox continues to inspire and intrigue people of all ages. By exploring the twin paradox, we gain a deeper appreciation for the elegance and strangeness of the universe as described by modern physics. It challenges us to think beyond our everyday experiences and consider the extraordinary possibilities that lie within the fabric of space and time. The twin paradox is a testament to the power of human curiosity and the endless quest for knowledge. Imagine a pair of identical twins, let's call them Alice and Bob. They share everything from their looks to their childhood memories, growing up side by side, inseparable. But as they reach adulthood, their paths diverge in a most extraordinary way. Alice decides to stay on Earth, pursuing a career in environmental science, while Bob, driven by a sense of adventure and curiosity, embarks on a daring space voyage. He joins a mission to explore distant galaxies, a journey that will take him far from home. Bob's spaceship is capable of traveling at a significant fraction of the speed of light. This advanced spacecraft, equipped with cutting-edge technology, allows him to traverse the vast expanses of space in a way that was once only the stuff of science fiction. This is where the strangeness of special relativity comes into play. Special relativity, a theory proposed by Albert Einstein, fundamentally changes our understanding of time and space. It suggests that the faster you move through space, the slower you move through time. According to Einstein's theory, time is not absolute but rather relative to the observer's frame of reference. This means that time can stretch or compress depending on how fast you are moving compared to something else. This means that time can pass at different rates for observers who are moving relative to each other. For instance, a clock on a fast-moving spaceship will tick more slowly compared to a clock on Earth. In the case of our twins, Bob's high speed will cause him to experience time dilation relative to Alice, who remains on Earth. While Bob might feel like only a few years have passed during his journey, Alice could experience decades. This fascinating phenomenon shows how intertwined and complex our universe truly is. Time dilation is a consequence of the fact that the speed of light in a vacuum is constant for all observers, regardless of their relative motion. This might seem counterintuitive, but numerous experiments have confirmed its validity. One way to understand time dilation is to think about how we measure time. We often think of time as a series of ticks on a clock. However, according to special relativity, the faster an object moves through space, the slower it moves through time. In other words, time slows down for objects in motion relative to a stationary observer. This effect becomes more pronounced as the object approaches the speed of light. Here's where the paradox arises. From Bob's perspective on the spaceship, it's Alice who is moving away at high speed. Therefore, according to the principles of special relativity, Bob should observe Alice aging more slowly than him. This seems to create a contradiction. How can both twins believe the other is aging more slowly? This is the crux of the twin paradox. It challenges our intuitive understanding of time as a universal and unchanging concept. The resolution lies in understanding the asymmetry of the twins' journeys. Section 5. Resolving the paradox, the importance of perspective. The key to resolving the twin paradox lies in recognizing that Bob's journey is not symmetrical to Alice's. Alice remains in a single inertial frame of reference throughout the experiment, that of Earth. Bob, on the other hand, must accelerate to leave Earth, decelerate to turn around, and then accelerate again to return. These periods of acceleration and deceleration mean that Bob is not always in an inertial frame of reference. This difference in their reference frames is crucial for understanding why Bob ages less than Alice. Section 6. Evidence for time dilation, from particles to astronauts. While the twin paradox might seem like a purely theoretical concept, there is ample experimental evidence to support the reality of time dilation. This phenomenon, predicted by Einstein's theory of relativity, has been observed and measured in various scientific experiments. The concept of time dilation suggests that time moves slower for objects traveling at high speeds compared to those at rest. This has profound implications not just for theoretical physics, but also for our understanding of the universe and the nature of time itself. One of the most compelling pieces of evidence comes from the study of muons, subatomic particles created in the upper atmosphere. These particles are produced when cosmic rays collide with atoms in the Earth's atmosphere, creating a shower of secondary particles. Muons have a very short lifespan, typically only lasting about 2.2 microseconds. However, because they travel at speeds close to the speed of light, the effects of time dilation become significant. Muons have a very short lifespan, but because they travel at near the speed of light, time dilation allows them to reach the Earth's surface where they can be detected. Without time dilation, these muons would decay long before reaching the ground. This observation provides strong evidence for the time dilation effect predicted by relativity. The fact that we can detect muons at the Earth's surface is a testament to the accuracy of Einstein's theories. Similarly, extremely precise atomic clocks flown on airplanes have shown minuscule but measurable time differences compared to clocks on the ground, confirming the predictions of special relativity. These experiments involve synchronizing atomic clocks on the ground and then flying one of them on an airplane. Upon the airplane's return, the clock that traveled shows a slight lag compared to the one that remained stationary. This difference, although tiny, is consistent with the time dilation effect. Such experiments not only validate the theory of relativity but also have practical applications in technologies like GPS, which must account for time dilation to provide accurate positioning data. Section 7. The speed of light, a universal constant. The speed of light plays a fundamental role in special relativity. It is not just the speed at which light travels, but rather a universal constant that governs the relationship between space and time. Einstein's theory postulates that nothing can travel faster than the speed of light in a vacuum. This speed limit has profound implications for our understanding of the universe. It means that there are fundamental limits on how fast we can travel and how far we can explore the cosmos. Section 8. Philosophical implications. Rethinking time and reality. The twin paradox forces us to reconsider our everyday notions of time and reality. It suggests that time is not a rigid, absolute concept but rather a flexible and relative one. This has profound implications for our understanding of the universe and our place within it. If time is not absolute, then our perception of the past, present, and future may be very different from the reality of the cosmos. Section 9. Conclusion. The enduring legacy of the twin paradox. The twin paradox remains a fascinating and thought-provoking concept in modern physics. It continues to inspire new research and debate among scientists. While the paradox itself has been resolved within the framework of special relativity, it serves as a reminder that our universe is full of surprises and mysteries that challenge our intuition. As we continue to explore the cosmos and delve deeper into the nature of space and time, the twin paradox serves as a testament to the power of human curiosity and our quest to understand the universe and our place within it.